What do you think happens when the massive stars that dominate the universe die? The death of a star is the most powerful single event in the cosmos, a blast so bright it can outshine entire galaxies. This isn't just a slow fade into the darkness. This is a catastrophic collapse, an invisible war waged inside the star, a war that for decades scientists simply couldn't figure out. The biggest stars in the universe live fast and die young. We're talking about stars that start their lives with at least 8 times the mass of our own sun. They run through their fuel-fusing lighter elements into heavier elements at a furious pace. They burn hydrogen into helium, then helium into carbon and oxygen. The pressure from their immense gravity forces these cores to get hotter and hotter, leading to the burning of carbon into neon and neon into silicon. The star develops a layered interior structure, sometimes called an onion skin structure, with shells of lighter elements fusing further out surrounding progressively heavier elements in the center. This chain of events is violent, but it sustains the star for millions of years. The immense energy released by the fusion process creates an outward thermal pressure that perfectly balances the inward crush of gravity. This balance is the star's entire existence, but this happy equilibrium is doomed to fail because of one element: iron. Why is iron the point of no return for a massive star? Fusion works by combining small nuclei into bigger ones, which releases energy. This energy maintains the star's outward pressure. But when the core finally produces iron-56, the rules of physics change completely. Iron-56 is the most stable atomic nucleus in the universe. If you try to fuse iron into something heavier, that process doesn't release energy. It actually consumes energy. It takes energy away from the core instead of adding to it. The star has hit the iron wall. It has run out of fuel. The pressure pushing outwards suddenly vanishes, and there is nothing left to hold up the star against the crushing weight of its own gravity. The star loses the war. The core begins a catastrophic collapse that will happen faster than you can blink. This core, which might be the size of Earth, begins imploding rapidly down to a tiny sphere, perhaps only 10 kilometers across, about the size of a city. This is the start of the supernova event, and for scientists, this is where the real mystery began, a mystery that took decades and the world's most powerful computers to solve. For years, the best models based on the known rules of physics kept hitting a wall, and that wall was silence. They couldn't make the star explode. If the very death of a star, one of the most powerful events we observe, couldn't be correctly modeled by our science, what were we missing? The iron core collapses at a speed that is truly terrifying. It accelerates inward until it slams into the neutron-dense center, a region so compressed that it resists further squeezing. This impact causes the core material to recoil, generating a shockwave that begins propagating outward. This shockwave, moving at immense speed, should theoretically smash through the outer layers of the star, lighting up the entire object in a glorious, powerful supernova explosion. But for decades in the simulations run by physicists, this is not what happened. The shockwave would start moving outward, but it would quickly lose energy. Why? Because the collapsing material from the outer layers of the star continued to fall onto the shockwave, dumping enormous amounts of energy into it. It was like trying to push a wave up a massive waterfall. The shockwave stalled. It stopped, or turned into an accretion flow, and the star fizzled out, simply collapsing into a compact object without the necessary explosive force. This was a major contradiction between theory and observation. We see supernova explosions constantly across the universe, roughly once every second of our Earth time, though many are too distant to observe directly. The core collapse supernova is a real event, yet the best, most sophisticated models based on standard physics were failing to produce it. The scientific community realized they were stuck in what many scientists call spherical cow territory. This means the early models assumed the star, and therefore the explosion, was perfectly spherical and symmetrical. When you draw pictures of stars, they are always perfectly round. When you write the equations for physics, it's easiest to assume that everything is perfectly symmetrical. But those assumptions kept the secret of the supernova hidden. For a quarter of a century, scientists grappled with this problem. If the physics were correct, and we had good reason to believe they were, then the assumptions about geometry must be wrong. The conclusion was unavoidable. The supernova explosion is not a clean or spherical event. The explosion is profoundly asymmetrical. It is messy, turbulent, and powerful in wildly unequal ways. But simply saying it is asymmetrical is not enough. Science requires proof and explanation. The scientists needed to find the hidden mechanism, the invisible agency, that successfully transfers enough energy to the shockwave to restart its outward propagation and trigger the explosion. They also needed far more computational power to deal with three-dimensional reality. The energy needed to revive the shockwave and produce the explosion isn't delivered by the bounce alone. It must come from the immense heat and energy trapped in the newly formed, ultra-dense core. This heat is escaping in one specific form. Ask yourself this: what tiny, nearly invisible particle is produced in massive amounts during core collapse and carries the energy needed to defeat gravity? The answer is the most elusive particle in physics, one that rarely interacts with matter at all, yet is the key to cosmic destruction. The neutrino. When the massive star's core collapses, it forms a proto-neutron star which is hot, dense, and releases an unbelievable number of neutrinos. Neutrinos are almost massless particles that interact very weakly with ordinary matter. They are so indifferent to the cosmos that trillions of them pass through your body every second, originating mostly from the sun, without you noticing anything. But in the extreme environment of a newly collapsed stellar core, conditions are so dense and hot that these neutrinos are produced profusely. This vast outward flood of neutrinos is what we call the agency of the explosion. If neutrinos interact so weakly, how can they possibly stop an imploding star? They provide energy through sheer force of numbers. As they stream out of the dense core, they deposit a fraction of their energy into the stalled shockwave above them, heating the material and providing the outward thermal pressure necessary to push the shock back into life. This is how the invisible war is finally won. The immense energy of the core, delivered by neutrinos, successfully fights the star's overwhelming gravity. This fact that neutrinos re-energize the shock was the missing piece of the puzzle that made the explosion possible in the sophisticated computer models. This discovery had a secondary, equally important consequence for astronomy on Earth. Since neutrinos are produced right at the center of the core collapse, they act as the starting gun for the supernova. They are released before the light does. The shockwave takes time to break out of the stellar envelope. In that time, the neutrinos have already escaped, traveling at nearly the speed of light. This time difference is not trivial. The time between the neutrino burst and the light appearing, called shock breakout, can be as short as 30 minutes or as long as 48 hours. This means we have an alarm system. Astronomers use this time difference to get a head start on observing the explosion. This led to the creation of the Supernova Early Warning System, or SNEWS. SNEWS is a network of massive neutrino detectors scattered around the world. These are huge tanks filled with water or other materials buried underground, waiting for the faintest signal of a neutrino burst. The system works based on extremely low probability. The rate of 2 different detectors seeing a random neutrino burst is incredibly rare, expected only once per century. If SNEWS detects a burst within about 10 seconds in 2 or more facilities, it immediately sends an alert to the world. This gives astronomers those precious hours to point telescopes at the right spot in the sky, observing the star before the light arrives. This early observation could tell us about the inner structure of the star right before its death. Information we can't get any other way, but while the neutrino energy is key, it only works if the core isn't perfectly round. The simulation must introduce complexity. It must be 3-dimensional to create the conditions where the neutrino heating can successfully overcome the stalling shock. This is where the concept of asymmetry fully enters the story, a concept confirmed not just in computers, but in the debris of ancient stellar deaths. The reason the shock stalls in a spherical simulation is that the inflow of material is perfectly balanced, making the outward push impossible. To break the stall, the simulation must introduce turbulence and convection. What is the only way to model the dynamics of massive stars and their deaths correctly? The answer is computational physics. Sophisticated computer models are required because the explosion is profoundly aspherical. These models, which can require more computer time than has ever been used by competitors, run in microsecond time steps and use millions of zones to tile space. The complexity is necessary to accurately model the physics, including gravity, nuclear physics, and particle physics. When these 3D simulations are run, what emerges is anything but clean. The stellar core is not exploding smoothly, it's bubbling. You see an asymmetrical blast where material is expanding rapidly out in one direction, while at the same time material is still falling back in on other sides. This is simultaneous accretion and explosion. This turbulence creates pockets, or bubbles, and when one of these bubbles wins and pushes out, it dictates the direction of the explosion. This asymmetrical explosion is the direct result of the core structure. The structure of the star itself, often referred to as its compactness, translates directly into the explosion's final product: the energy of the explosion, the mass of the object left behind, and the kicks it's given. The asymmetry in the explosion provides a crucial piece of physical evidence that we can look for. If an explosion is asymmetrical, the leftover compact object must recoil in the opposite direction due to the conservation of momentum. What evidence do we have that the surviving neutron stars have received a violent recoil? We can predict that the neutron stars should be given kicks, and the simulations predict a wide range of kick magnitudes, from modest kicks of 100 km per second up to 1,000 km per second. This range matches what astronomers observe. If the explosion had been perfectly spherical, the remnant would not have moved at all. The very fact that these stellar corpses are zooming around the galaxy is proof that the invisible war was fought asymmetrically. The sheer power of this destructive process goes beyond movement. It is the source of all the heavy elements in the universe. When a massive star explodes, it becomes the ultimate alchemist, scattering its mass into the galaxy. The explosion pushes the star's outer material, called ejecta, outwards at speeds around 20,000 km per second. This explosion does two things. First, it creates heavy elements, a process called nucleosynthesis. Second, it scatters those newly created elements. The blast wave, as it propagates outwards, heats the material in its path and triggers thermonuclear conversion, producing radioactive elements like nickel-56. Nickel-56 then decays into iron, which is the ultimate source of iron in the cosmos. Supernovae also scatter lighter elements that sustain life, such as oxygen, nitrogen, and carbon, which make up DNA. To confirm these violent 3D events, astronomers turn their attention to supernova remnants, the debris fields left behind thousands of years later. These remnants are resolved objects, meaning we can actually see their 3D structure. Unlike distant supernovae, which appear as mere dots, a prime example is the supernova remnant Cassiopeia A. Observations of Cass A show beyond any doubt that the explosion was not spherical. We can analyze the structure of the ejecta, the material blown out by the star, across various wavelengths. From X-ray to infrared, studies of Cass A and other remnants reveal the internal mixing of elements. For instance, X-ray data shows large amounts of reverse-shocked iron that have been pushed back into the debris cloud. If the star had exploded cleanly and spherically, we would expect a smooth distribution. Instead, the complexity of the internal turbulent flows and asymmetries means that elements like nickel and iron are distributed chaotically, something the latest computer models are struggling to match quantitatively. This research is highly important because these local remnants act as calibration sources for understanding distant, high redshift galaxies which only appear as blobs in the sky. If scientists cannot figure out the structure of a nearby object like Cass A, they cannot possibly interpret what is happening in the distant universe. Once the violence subsides and the ejecta rushes outward, the real question remains: what corpse is left behind in the center? The answer depends entirely on the mass of the remaining core. After the core collapse supernova, the immense gravity of the remaining core attempts to finish the job that the initial collapse started. Whether gravity succeeds depends on one thing: how much mass is left over. If the remnant core has a mass between 1.4 and about 3 times the mass of the Sun, the crush of gravity is stopped by something called neutron degeneracy pressure. The resulting object is a neutron star. Neutron stars are tiny, dense objects, only about 10 to 20 kilometers in diameter. They are so compressed that the density of this matter is extreme. Neutron stars are often found spinning incredibly fast, and when their magnetic fields align, they emit beams of energy we detect as pulsars. These objects are a direct result of the invisible war being stopped just shy of total gravitational victory. But the history of the explosion itself is recorded not just in the neutron star's kick, but in the neutrino detectors on Earth, the SNEWS network. Those detectors searching for the starting gun continue to operate 24 hours a day. Why is SNEWS considered a race against time? The goal of SNEWS is to get the alert out within seconds of core collapse. The time window that follows, from 30 minutes to 48 hours, is a precious, once-in-a-lifetime opportunity for astronomers. If a galactic supernova happens, literally every relevant telescope around the world will be focused on the coordinates provided by SNEWS, waiting for the light to catch up. The neutrino signal itself, if detected in sufficient numbers, can be analyzed to tell scientists a lot about the inner core. Each collapse model has its own distinct neutrino-like curve, which is systematically dependent on the star's initial compactness. By observing the characteristics of the neutrino burst, scientists can figure out what the inner core was like in a way they cannot do now with any distant supernova. However, if the surviving core is too heavy, the story changes completely. There is no known force that can stop the gravitational pull, and the invisible war is lost entirely. The star collapses into the most extreme object in the universe, a black hole. If the remaining core of the massive star is too massive, if it exceeds approximately 3 times the mass of the Sun, the crush of gravity is so powerful that nothing can stop the collapse. Not even the mighty neutron degeneracy pressure can hold against it. The star disappears into a region of infinite density called a singularity, enveloped by the most famous boundary in astrophysics: the event horizon. The event horizon is not a physical surface. It is a boundary in space-time where the gravitational pull is so strong that the escape velocity, the speed required to break free, is greater than the speed of light. Once anything, including light, crosses that boundary, it is gone forever. Black holes, while often complex in their behavior, are surprisingly simple to describe. It might surprise you to learn that scientists can characterize a black hole using only 2 quantities: mass and spin. That is it. These are the only numbers that describe a black hole in the universe. Everything else about the object is lost. Black holes are typically organized into 2 main size classes. 1. Stellar mass black holes. These are the ones formed from the collapse of a single star, usually measuring 3 to dozens of times the mass of the Sun. And 2. Supermassive black holes. These are the gigantic monsters found at the center of nearly every galaxy. They range from millions to billions of times the mass of the Sun. The existence of supermassive black holes presents a problem for astronomers. If we look at the most distant quasars, which are the active black holes in the early universe, they already have very, very big black holes in them. The question is, how did they grow so quickly when the universe was still young? One idea is that many stellar mass black holes simply fall into each other and merge into a large black hole. Another idea is that a large cloud of gas collapses directly to form a supermassive black hole in one go. But regardless of size, the major challenge remains. How do you study an object that absorbs all light and is completely invisible? The answer is through strong field relativity, observing the immense indirect effects these objects have on the matter and space-time around them. To observe a black hole, you must look for light that is emitted before matter crosses the event horizon. For stellar mass black holes, we look for them in X-ray binary star systems. An X-ray binary is a system of 2 stars in orbit around each other, where one is an ordinary star like the Sun and the other is a compact object, either a neutron star or a black hole. The immense gravity of the compact object strips gas and material off the companion star. This material spirals into a rapidly rotating structure called an accretion disk. The gas in this disk is compressed and heated by friction to millions of degrees, causing it to emit huge amounts of high-energy radiation, primarily X-rays. These X-ray sources can be incredibly bright, and thousands of times the total radiation seen from the Sun, all coming from a region substantially smaller than Earth. Astronomers use orbiting X-ray observatories such as Chandra to detect this high-energy light. These satellites are crucial because they see the universe not in visible light, but in X-rays, which are produced by the hottest gas and most energetic processes. The key to proving that the compact object is indeed a black hole and not a neutron star relies entirely on mass. What is the minimum mass required for an invisible object to be definitively confirmed as a black hole? Scientists measure the orbit of the companion star, which allows them to calculate the mass of the unseen object. If the mass calculation is greater than 3 times the mass of the Sun, it is scientifically confirmed as a black hole. The upper limit of 3 solar masses is what separates a neutron star from a complete gravitational collapse. But X-ray observatories can tell us even more. X-rays emitted from iron atoms swirling near the event horizon are affected by the black hole's gravity and rotation. By observing the distortion or the smeared-out appearance of these X-ray light features, astronomers can estimate the spin rate of the black hole. The faster the spin, the more warped the X-ray light appears. This is all part of a broader study of strong field relativity, effects that are totally different from Newtonian physics and only happen close to the event horizon. This same process of accretion also powers the largest structures in the universe, supermassive black holes. When these central objects are actively feeding, their accretion disks shine brightly and we call them active galactic nuclei or quasars. The power source is the gravitational potential energy released by the matter falling onto the black hole. In some cases, the infalling matter doesn't just disappear. Black holes can launch incredible, collimated beams of plasma called astrophysical jets that stream outward from the poles. These jets are strong enough to get out of their own galaxy. What force is strong enough to accelerate these jets across intergalactic distances? These powerful jets are thought to be powered by strong magnetic fields within the accretion disk. The magnetic fields accelerate particles, leading to enormous energy output. These jets influence the entire galaxy, controlling its formation and stopping it from growing too big by blowing away its gas reserves. This strange interaction is often described as a love-hate relationship or a symbiotic relationship. The discovery and successful modeling of core collapse supernovae have fundamentally shifted our understanding of gravity, physics, and the composition of the universe. It required decades of work and the world's most powerful three-dimensional simulations to prove that the invisible war inside a massive star is profoundly asymmetrical. Without this destructive asymmetry, the shockwave would stall, the explosion would fail, and the heavy elements would never be scattered, if you want to understand space. Like a NASA-level analyst quick without studying for years or paying thousands for a university degree, we have a community that will help you. Link is below. Every time a massive star explodes, it acts as an extreme astrophysical laboratory. This is the violent furnace that creates the elements of life, the elements that make up our bodies, the gold in our jewelry, and the oxygen we breathe. The entire story of cosmic destruction is also the story of cosmic creation. If you want to follow up on this idea, how this spectacular asymmetrical death provides the essential ingredients for life, click the video on the screen now for How Stars Create Life and discover the final beautiful payoff of stellar evolution. I'll see you there.